One of the many things that fascinates me is hysteresis. A good familiar example of hysteresis is thermostats. The idea behind a thermostat, if it's working properly, which it isn't for me right now because it's too damn cold, but if it's all working properly, then the temperature in the room drops and drops and drops and drops and drops, and eventually the thermostat turns on, and the heater turns on, and then the temperature in the room starts to rise, and then it gets to a certain point, and the thermostat turns off. And so the temperature in the room is doing this. You don't want, in a lot of electrical systems, you don't want a signal to be on should some condition be met and off should that condition fail to be met, because if you're right on the boundary, you can end up in in-between states. Am I quite on or quite off? I think for a thermostat, which is electromechanical, the problem you would have is electrical contacts almost but not quite meeting and causing sparking, which would erode the contact surfaces or cause them to stick or do something else unpleasant like that. And so, for other reasons as well, but in my mind, for that reason in particular, you want a thermostat to have hysteresis to it. Now, the real solution is to have more control over your heater than just on and off, and have something like a PID loop. Anyway, it's out of scope. Right now we're talking about hysteresis because I made a crappy little video of this crappy little invention, which is a busted flashlight, crank flashlight, with a circuit that implements a boost converter and 3 neon bulbs. And the boost converter takes the low voltage out of this guy and brings it up to a high voltage so that you can run neon bulbs. I'll show you what this is all about if you haven't seen the other video. And after I made the first video, I realized I really ought to make a video about the hysteresis that the system exhibits, because neon bulbs do have hysteresis. It's actually quite fascinating. It takes a high voltage to ignite these bulbs. These in particular, I haven't measured the voltage, but I think another one that I was experimenting with would ignite around 100 volts. But once it's lit, it continues to be lit, even as the voltage drops below what was required to initially ignite the bulb, and then down around 70 volts for the bulb that I had measured. It would eventually go out. So this circuit charges this electrolytic capacitor, and the neon bulbs, which are in series, are wired to this capacitor, and so when the voltage on this reaches a certain point, they all turn on. And then, even as the voltage here drops, they continue to remain lit. I have an interesting way to demonstrate hysteresis here, besides just charging it up and watching it run down. I'm going to turn the crank a few more times, and that's going to make the voltage on this electrolytic capacitor go up somewhat, but I'm not going to turn it enough times that these light. And then I'm going to do something a little unusual, and I will reignite them, and then I will discuss what just happened. Okay, what just happened there? Well, when these go out, they by and large stop conducting current. There is a small current. I know this because with the lights out, you can see one of these glowing slightly, but for all practical purposes, they really don't pass any current when they go out. So, the voltage here remains about the same. I turn the crank a few more times and it goes up, but not high enough to light all 3 bulbs in series. However, when I touch the 2 terminals on this bulb, I essentially short across it. And so now, the voltage required to ignite the neon bulbs is not the voltage required to ignite 3 of them in series, but only 2 of them in series. And so I do that, and then I let go of the middle bulb. And since the voltage that these run at is lower than the voltage they ignite at, the voltage across the 2 terminals of this middle bulb is sufficient to ignite it, which is kind of cool. And so then they are all ignited and all continue to run until they get down to that voltage where they stop operating. So if we wait for the voltage to drop and they go out, and I do this again without cranking this, will they all remain ignited after I let go? Well, no. I can make these 2 ignite, but they just go out again when I let go because the voltage is not sufficient to ignite this one. That's a curious little experiment. And just one of the things that continues to delight me about hysteresis. There are some fascinating military training videos. Actually, I think they're Air Force, showing the latest cutting edge in technology from World War II or thereabouts. I'll try and link to these videos, but they show an application of hysteresis which wasn't really obvious to me, but once I saw it explained, I was instantly fascinated. And that is that you can use hysteresis to do logic operations. And in particular, I was able to find some research papers that discussed how you might build logic gates out of ferrite toroids. Did I mention? Yes. No, I don't think so. Well, these videos, they're about so-called core logic, but you've got these little beads, little toroids, made out of a ceramic sort of material called ferrite, which can be magnetized. So you can have a magnetic flux, a field, going around this way through the bead, or this way through the bead, and when you're not applying any magnetic field from an external source, it will retain that field. Anyway, you can do logic with that, apparently. It's quite cool. You need diodes as well. You can't just use wire and beads. You need diodes. But those are pretty primitive technologies. You don't need any transistors. Very robust and durable too. Maybe you could make computers that would, survive horrible catastrophes like crash of the space shuttle. Some core memory survived. Core memory is an application of these ferrite beads in hysteresis that was widely applicable for quite some time. Basically, you arrange these beads in a grid, and then using wires passing through this grid, you can cause magnetic fields to remagnetize these beads in one of their two orientations. And then you have a sensing wire that passes through the grid, and you try and remagnetize the bead, and if you make the field go this way, and it's already magnetized this way, then the flux, the magnetic flux, won't change all that much when you do this. But if the bead, say, is magnetized this way, and you try and remagnetize it this way, then the field flips, and all of a sudden you get this big change in the magnetic flux, and that is what causes a voltage to be generated, or current to be generated on your sense wire. Well, it has an impedance, and so voltage and current are related by that. And so you know what state it was previously in when you did this, so you're able to read the memory, and then you just got to make sure if you didn't want to change the contents of the memory when you did that, you have to set it back to how it was. But core logic never really seemed to take off. Core memory, yes. Core logic appeared to remain mostly theoretical. I've never seen a device which uses ferrite beads in this fashion. It's something I've always wanted to experiment with, but I think it'd be rather difficult. Finding ferrite beads with the right magnetic properties, and even defining what the right magnetic properties exactly are, isn't exactly one of my skills. I suppose I could develop that skill, but at some monetary cost, which I don't like. That's why I like programming. It's cheap. Except at work. They buy us a lot of software to do our job. I love Visual Studio and Team Foundation Server and all those, but I think, God, it's so expensive. What was I talking about? Oh, right. I think you could implement logic with neon bulbs as well, because they exhibit hysteresis. And I think, like magnetic core logic, you would have to employ diodes to do this. I've tried to figure out how to do it without diodes, and I've not succeeded. So I think I'm going to give another stab at it with diodes and see where I get. And then maybe I'll be making another YouTube video. Maybe even with a built circuit. That would be cool. Now, my understanding of the core logic is that it doesn't work in the same fashion that, say, TTL or CMOS logic does, in that you don't have signals which are continuous and then the output state is determined by the present input state. Instead, the computations are done on the transitions, which would suggest to me that these technologies that employ hysteresis to do logic might be amenable to things like asynchronous state machines. And I read a paper recently by a Professor Scott Houck, who taught one of my introductory digital logic courses when I was a sophomore, I think. He talks about asynchronous state machines and sort of reviews the techniques for designing asynchronous state machines that have been proposed in existing papers, and don't know if I finished reading the paper, but I don't think he proposes anything new. I think it's just a review of what already exists. One of the things that I find rather lacking in the current research is it's observed that under certain models it can be useful to send your state and then receive an acknowledgement of receipt of that signal before you are allowed to send again. And then it's said that, well, you've got a wire, say, that goes from here to here, and it can have two states, and you transition from 1 to 0, then clearly you've said, now my state has become 0. And if you transition from 0 to 1, you said my state has become 1, but what if you want to say, I performed a computation and my state was 1 and it continues to be 1? Well, clearly this paradigm doesn't work, because you can't send a signal saying that you're already at this, or that you are transitioning to the state that you're already at. Well, that's not true. You just need 2 or more wires. 2 is the minimum number. I'm rambling. I just think that the problem is completely tractable, and that research paper sometimes kind of missed the mark in my view. Not commonly, but asynchronous state machine seems to be one of those things. I was going to end this video better in my previous attempts. This is like the 3rd time I've tried to make it. Every time I end up rambling. I think I'll work on my neon logic some more and see where I get, and maybe make an asynchronous state machine and yeah, just have fun.